lapsed. Sam.
Hello, there we go. So I've been assigned a 30-minute slot for this. I don't know that I will fill 30 minutes, but I will give it my best. I need to share my screen.
You need not. As it turns out, we are good for time, but please feel free to break off early if you care to.
That sounds good. What I need to do, though, is first thing I need to do is bring up my let me address that. So I posted a link onto the mailing list for SVFIG, and in that link, you will find, as soon as I share my screen, I think we want to do that. Oh, I think that worked. You'll find this webpage here. This is a GitHub repository, correction, not GitHub, but it is a Git repository of everything that I could recall in the matter of maybe about 5 or 6 hours of the Kestrel-1. Now, a lot of people in the fourth world probably remember me working on Kestrel-2, Kestrel-2DX, and later the Kestrel-3, but very little love and attention has been given to the Kestrel-1. And part of that is because it was never really intended to be a complete computer unto itself. It was basically just a, what's the word I'm looking for? Proof of concept. And so it was taken upon myself in 2004 to actually finally go out and build myself a computer of my own design. And I needed to make it as simple as I could possibly make it. And of course, I chose a processor which was not exactly known for being as simple as possible. And that is the 65816 processor, which is the 16-bit upgrade to the 6502. The reason why these CPUs are not as simple as they could be is because of how they lay out memory and the fact that they only have memory mapped everything. So if you want to access I/O, that has to be mapped into memory as well, which means a simple system needs at least 3 items on the bus. You have RAM, you have ROM, and you have I/O, and therefore that necessarily means your address decoding is maybe a little bit more complicated than it needed to be, compared to, for example, a Z80, which has a split memory map for both memory and for I/O, and you could rely on that very easily in hardware. So the way I solve this problem, I'm going to open this with Document Viewer, and then I'm going to, hello, let's not do that. There we go. So the way I solve this problem is very simple, and I basically just got rid of ROM. And the entire computer system has only 32K of RAM, and it has 1 I/O chip, and that's it. The RAM occupies the same space that ROM would normally take. So in other words, it sits high in the address space instead of conventionally at low addresses. And so when you program this thing, you basically write your software so that the start address of your software sits in the reset vector of the processor. And then in low memory, where you would typically have 0 page and stack, you have this I/O chip, which is replicated for 32K. this single 7400 chip is the entirety of its address decoding logic. It addresses RAM versus RAM versus the I/O, but it also separates out the single read-write. Where is it here? There we go. The read-write pin here, and gates it against the phase 2 logic, and that then gets broken out to the chip select, output enable, and write enable pins here. This is a 6500 series I/O chip, so I really didn't have to do anything in terms of address decoding. In fact, I basically just use A15, the high bit of the address bus, directly as its low chip select. And so the only really missing piece here was the clock, the 4 megahertz clock. That's just a regular 14-pin metal can clock oscillator. Not much going on there. And that's basically it. That is the entirety of the computer. You'll notice that there's nothing connected to the other side of the I/O chip. And that's mainly because my proof of everything working was to hook up oscilloscope probes to the various I/O pins and not much else. I really didn't, at the time, didn't have an understanding of the 9P protocol, for instance, that I could have used over CA1 and CA2 as a serial protocol, for instance. To actually program the circuit, what I did was I built up another a serial to parallel interface using TTL shift registers, the 74LS595 chips. I had 4 of them. Now, the exact pinouts might not be exactly as I had them back in 2004, but everything here is what you would need to actually program it. And what you would do is you would basically use the serial input, and you would basically pulse 32 bits per bus transaction into these registers. And then you would assert, and then you would pulse the load pin here. And what the load pin does is, after you've shifted all 32 bits into the holding register, boom, you in parallel, you would update all 4 parallel outputs at once. So from the perspective of the processor, or I'm sorry, from the perspective of memory, it looks like a 6502 or 65816 is driving the bus. To prevent bus contention, I had to have another pin here called BE reset, and that connected to this the processor's reset pin and the BE line. Now, one of the advantages of the 816 over the 02 is DMA capability. It has bus buffers actually on chip, and so the BE pin controls the output enable of those buffers. With the 6502, I would have had to use external buffers. Regardless of how that's done, the point being, you could tie reset and BE together such that when the chip is in reset, it's also taken off the bus, which allows me to use this circuit to drive the RAM chips. As long as this pin remains low, I can do that. When this pin goes high, thus re-enabling the bus drivers on the processor, and also taking the processor out of reset, this circuit here becomes ineffective. Now, what I did not show on this schematic is there are resistor packs that go in line with these pins. Any value will work. I used 4.7K if I recall correctly, but you'll need 25 of these resistors, 1 for the read-write pin and then 24 for the address and data bus. And that is because I did not at the time have output enable controlled by the BE reset. So in this circuit schematic, I fixed that bug because I realized as I was drawing up the schematic, that the output enable pin could just be tied to this pin as well. Problem solved, right? If only I'd known that back then. So technically, this is actually a simpler circuit than what I ended up with back in 2004. But yeah, what this circuit is literally the first Kestrel. Oh, thank you. And programming it involved, writing some custom software that ran under Linux. Oh, that reminds me, the timing in the protocol. Let's see here. Zoom in on this a little bit. The protocol, I hope you can read that, but if not, it is on the PDF. You can zoom in locally. It's very, very simple. Essentially, what it boils down to is the first thing you need to do is set read write to high. In other words, you want to read from the bus. Then negate the BE reset pin so that you put the processor into reset and therefore unable to drive the bus. Once that quiescent condition is established, you would then blast 32 bits into these shift registers to load D0 through D7, your data bus, and A0 through A15, which is your address bus. Then you would pulse load. At this point, your read-write is still high. You're not actually writing anything at this point. Then you would do that whole thing all over again, but this time bring read-write low. And then you would do it again, this time bringing read-write high, right? So basically the idea is data and address buses are guaranteed to be stable when you pulse read-write. And then you do that for as many times as you need to, for as many bytes. And then once you're done, you just assert BE and reset again, and that brings the processor back online. If you notice that this is essentially what you would do by hand, flipping toggle switches on like an Altair 8800, except it's manual. It's manual on the Altair 8800. With this, I have a special programming circuit to do that. But otherwise, it's yeah, that's the entirety of the computer. This is what got me off on the trajectory of working on various Kestrel machines. One of the things that I realized as I was drawing up the schematics for this is, I still have 7 of those CPU chips in my garage. And I have an RC 2014 sitting on my workbench in the garage as well. This circuit is actually simple enough that I might try, especially with my FPGA knowledge now, I might try throwing an FPGA in the loop so that it does address decoding and maybe bridges the bus between the 65816 and the Z80 bus. But I might try making this into a plug-in card that I can use with the RC 2014. It's no guarantees. I mean, obviously, I haven't done anything computer related in a long time now, but slowly but surely things are getting done. But just another project on the back burner, I guess. But it's just an idea, here's a processor, a simple RAM, and in fact, nowadays you can get for the cost that I paid for the 32 kilobytes of RAM, you can now get 512K chips for the same price nowadays. And then maybe replace this VIA chip with the FPGA circuit and use that to drive the RC 2014 bus. And that's probably something that I would do. The original design for the Kestrel 2, not the one that I showed at SVFIG, but the original Kestrel 2 concept, like if I were to go back in my notebooks, is basically this circuit, but equipped with video output, so that basically I could drive a VGA monitor with 320 by 200 with 256 colors or something like that. Something fairly simple that I could have accomplished at the time. And yeah, so that is the Kestrel-1. That is the circuit that got me off on the Kestrel bandwagon, so to speak. Any questions?
I'm less familiar with the variant of the 6502 you're using, but I assume it gives you the ability to move the stack away from its traditional location at page 1 into some other place.
Yes, it does. The 65816, you can move both direct page and the stack independently. The only constraint is that they must reside within the first 64K of memory. The chip itself is capable of addressing 16 megabytes, but unfortunately, those two items, while they can reside anywhere in the first 64K, unfortunately are constrained to that bank, as it's called in the documentation. Cat, do you mind? I have a fat cat here who's like trying to interrupt me here. I should point out there is a, let me go back to the schematic here. There is an additional feature which not many people make use of, and that is that pin right there, the abort pin. That is a third type of interrupt on the 65816. And it's unique from IRQ and NMI in that if this interrupt is asserted, the currently running instruction has its register write back curtailed. So program counter does not increment, accumulator or index registers do not get updated, and the flag register does not change. But you still take the interrupt as you normally would. This is awfully, incredibly useful. You might think to yourself, well, why would I want to do that? I mean, if I interrupt an instruction versus between instructions, that means that I can restart that instruction later. And if I can do that, that means I have virtual memory capability. So with an external MMU, a memory management unit, I can actually implement, 4 kilobyte long pages or even 256 byte pages. And I could swap between slow memory and fast memory, or hard drive and memory, etc. So realistically speaking, if you're building a system that uses this chip and you're constrained by the 64K limitation for direct page and for stack, you can actually work around that by using a memory management unit and that abort pin. Really handy, because then you basically have multiple address spaces at your disposal, just like you would in, say, a more traditional Unix environment, for example. So it's actually pretty cool. This chip is unexpectedly flexible. I see that there are some chats. Let's see here. Okay, yep, nothing related there. So yeah, that's the Kestrel-1. Schematics are online. It is licensed under an open hardware license, the TAPR open hardware license, actually. Yeah, have fun.
What fond memories. So I think we're ready to get into this month's challenge. Bill Ragsdale will moderate.
You're muted, Bill.
There we go. We call that the muting button. We call that the spousal control around here. So we have